Okay, here I have some data. So on the left I have the DNS data on a mesh like this example, just a illustration. So let's say I have a extremely tiny mesh on which I have computed this DNS. Now I take the LES filtering operation on the DNS data. That means now my mesh is like this. This is the filter. This is the filter size. This is the DNS mesh. Okay. So now on a larger filter size or on a mesh you can think of, I am filtering the DNS data. So then this is how the data looks like. Obviously it is smeared out. I told you filtering is nothing but low pass filtering we are talking about. So what is low pass filtering? The low frequency signatures of your turbulent eddies are passed. The tiny eddies have high frequency signatures. Those are filtered out. Low pass means allow the low pass signatures, filter out the high frequency. So the high frequency tiny. So you can see that here. If you compare DNS figure and the DNS filtered, obviously it is smeared out in the DNS filter, right? Tiny information is gone here because that volume averaging has occurred. The low pass filtering has occurred. But now if I use the same LES, this DNS filter size, if I use the LES calculation, this is filtered, this is resolved. You can see the difference here. Now since the residue is not exact, it is modeled. So model effect has come in LES, right? So compare the figure between these two. You see that it is even more smeared out. Some more information is lost. That is because of the modeling. The modeling error has been introduced in the LES case. Same mesh. Okay, same mesh. One is DNS filtered, the other one is LES resolved. This gives the clear picture what is the difference between filtering and resolving. Okay, this is clear. Okay, so now we will mathematically see what we mean by this resolving, filtering and modeling. For that we apply this concept to the governing equations. Okay, all right. Yes, yes. So the mesh size is same. So this LES mesh or the filter size, it is able to capture whatever it could. That means eddies that are larger. The tinier one has not been captured by LES, so they are modeled. So that model error has resulted in some loss of information in this graph in the LES. But in DNS, same mesh is used to volume average the data, and then since the residue is exact, some information that modeling error is not there. There is still no loss of that information. Okay, this is clear. Okay, so now we'll see a little bit more in depth what we mean by this low pass filtering, volume averaging and so on. So I can give an illustration here. So let's say I have a signal, a 1D signal. Okay, so let's say I have phi is my random signal. Let's say it looks like this. Along x direction, I look at a 1D signature of a random component phi. If I do low pass filtering, so there is high frequency noise here, and of course there is some low frequency turbulent signature also. So if I am going to do that, if I set a filter size, let's say I set a filter size like this. Let's say this is my delta. Delta is the filter size, let's say. Then if I do a low pass filtering or volume averaging, this signal would look like this. So this is phi bar. It is still random. The phi bar is the filtered component. By volume averaging the data of a filter size delta here. Okay, I can say like this, use an arrow mark. Based on, if you change the filter size, the signal will look different. Or how much, what is the cutoff frequency here in the low pass filtering, your signal will look more and more smooth. More frequencies that you are cutting it off, it looks more smooth. It may even become a actual like sine wave like looking thing, right? But as long as, that means you decide here. So in LES, the user has a bigger dependency on choosing the mesh and allowing how much to be captured, right? And in principle, you must capture all the large eddies except the dissipative eddies, everything you must capture. If you don't, then your model is not capable of giving good results, because what you are modeling is only the dissipative eddies. Their role is very clear. They have to capture only the effects of, or the SGS models are only meant to account for the dissipative eddies. If your mesh is very very coarse in LES and you are asking your SGS model to account for even inertial range eddies, obviously LES results will be bad. Your simulation results will not look good because the model is not capable of doing that. So this filter size is something you have to choose. Anyway, so now the context of subtracting the mean, if I get rid of the mean here, then you will get the fluctuation phi prime. Okay, then the phi prime would be like this, let's say, and if I filter the phi prime, it would be like this. This is my phi prime over bar. Now over bar is filtering, not ensemble averaging in LES. Okay, so the phi prime over bar. So this is the filtered fluctuations here. This is not phi double prime. I'm doing like decomposition here. I have the instantaneous signal and the fluctuations phi prime, and I'm doing filtering on both. Let's say the DNS data is this black phi and phi prime, and I do filtering, low pass filtering or volume averaging, I get phi bar, the red, as well as the fluctuations phi prime bar. So this is the instantaneous and this is the fluctuations here. So this phi prime over bar is your filtered fluctuation. Okay, and the phi bar is, as told you before, it's just a filtered random component here. Is this clear in the illustration context? So now this is a 1D filter that we have applied. So you can say that we can define what we mean by the filtering here. Already told you that it's a low pass filtering. Filtering is nothing but filtering or volume averaging. So for a 1D, if I define this, it looks like this. Phi bar is given by so I have phi bar of x comma t, so one dimensional, need some space, let me do it here. In 1D, the phi bar of x comma t will be equal to 1 over delta x, the filter size in the x direction, okay, integral x minus delta x by 2, x plus delta x by 2, your phi dx. This is the filtering or volume averaging that you are doing over delta x is the filter size along the x direction. We will do a generic 3D filtering later, just to understand the 1D filtering that I have just shown you in the schematic diagram here with the oscillations. This is how a filtering operation would look like, volume averaging in one dimension. Okay, so 1D average or filtering. Okay. So now we also look into we have looked into the differences between the RANs and the LES. In the context of it, we'll also look at some more differences between the RANs and LES before we go into the governing equations. Okay, again, RANs versus LES. So in RANs, we know that we do ensemble averaging. So that means the phi prime over bar. Here over bar is the ensemble average, right? So ensemble average component of phi prime, what is this? 0, right? Ensemble average of a fluctuation is 0. No need to prove this, it's already been done in the class before. But in LES, phi double prime is our residue and over bar is the filtering, volume averaging. What will this be? Is it 0 or non-zero? It is in general non-zero, except in spectral filters. When I discuss the types of filters, I'll discuss this. Except in spectral filters. So in general, phi double prime or the volume averaging or filtering your residue is not going to give it a 0 value. So that means phi filtering is not equal to phi double filtering. Okay, so this is filtering, this is double filtering, even on the same filter size. This is not ensemble average. In the RANs, it was the bar represented ensemble average. So ensemble averaging and ensemble average quantity doesn't change anything. It has achieved its true mean. But here the bar represents filtering in LES. Okay. So this is the primary difference here. Even for this is even for same filter size delta. We will discuss this in detail later when we discuss the types of filters, what are the exceptions, how we can say that double filtering is not same as filtering once, or any n number of filtering operations you do, the data would change slightly. Okay. And also we also had this in the context of DNS filtering and LES. I just forgot to tell you here. Yeah, here the phi the DNS and the LES part here. Here I only if your LES model is so good, then only this phi double prime will be same as phi double prime exact here, right? If I look, I'm looking into the black symbol here, phi DNS is equal to this part. So here if phi double prime exact residue, if it has to be equal to phi double prime in the LES, that means your LES model is so good that it is able to capture, and usually it's not usually, and just say it will not be like that, and therefore these two are not the same, just a note. And we can go back to the equations slightly to see how we proceed. Any doubts on this before we move to the governing equations? Why are we filtering phi prime? Phi prime is the fluctuation, turbulent fluctuation. Yes. Why are you doing what? Complete the question. I want to filter it, the signal. Let's say I have the DNS fluctuation data. I want to volume average it to see what it looks like, because I want to compare what the fluctuations captured in LES will look like, right? So LES is an eddy resolve technique that I mentioned, just like DNS. But here there is a modeling component, unlike DNS. Like some turbulence modeling has to be done here for the dissipative eddies, and therefore you are interested in capturing the random component in the LES. It is not statistical approach. You are actually computing the actual turbulent flow the way it looks like. Some modeling errors are there. So obviously then you have to do Reynolds decomposition to get mean and fluctuation. In RANs, mean is directly accessible to you. When you are computing any quantity, you are computing only for the mean pressure, mean velocity, right? So the turbulent component you have no access, it is fully modeled. But when you run LES, by default you are running for random velocities and random pressure quantity. If you want mean, you have to do post processing, you have to do an averaging operation, a time average or whatever you want to do it, to get a mean velocity and a mean pressure and separate the fluctuations. From the separated fluctuations you can get Reynolds stresses, right? That's the whole point. So the overbar has a different meaning here. So when we take this concept to governing equations, you will understand what we mean by that. That means you are filtering it again, like I showed you in the graph, right? So I have the DNS data, let's say I filter it using an LES filter size. I do that operation again on the same filter size, the data will change. It may sound strange. If filter size is changing, yes. If delta becomes 2 delta, obviously the results will change, or 3 delta, 4 delta, it looks more smeared out, right? I agree. But even for same filter size, it occurs, except spectral filters. Each time you do volume averaging operation, this would occur. So this is more like let's say you have this room is divided into, let's say you have temperature probes here for every 1 meter, and you are getting, let's say, some 10 by 10 measurements, some 100-point temperature measurements you are getting thermocouple. Let's say if I divide it into only 2 by 2 now, right, you are going to average whatever is there in that particular, you are going to make it into 4 squares, let's say, and all the thermocouples in that big square you are going to average. So some information is lost there, right? But here you are assuming that you have 10 by 10 thermocouple data and you are doing some averaging over a volume. But what if you are asked to compute only for this 2 by 2 components temperature? Obviously it will not be same as the averaging the data that is sitting in that from the 10 by 2 filtered to 2 by 2. How is the large eddy becoming small eddy? I don't know why it is, how it is becoming, why is becoming, how, okay, how maybe I can explain why it is becoming is, this is little difficult to say. The vortices or the eddies do break up, there is shear, right? It's eventually turbulent flows are shear flows, so there is shear. If you take two counter rotating eddies, there is a shear between them, and we are looking into high momentum or high inertial, right? Reynolds numbers are very high, so inertial effects are dominating over viscous effects. So you have shear, you have nonlinear interactions, so the vortices do break up. Many factors are there. They can amalgamate also, they can form a bigger eddy, break up again. We are not introducing any scales inside the governing equation, right? The governing equation doesn't know about the scales. Only when you simulate it knows about it, because you are giving a numerical mesh size and it is able to capture only vertical structures that are larger than the mesh size. Okay, so then we'll see tomorrow with governing equations.